Okay, well, welcome all. I hope people are having good, relatively quiet summer. So what I wanted to do is start off sort of open-ended since we're just continuing the last session. And so I wanted to start off with you. If since the last session, any questions or comments have occurred to you, why don't you volunteer them before we go on to, my questions? Does anyone have questions or comments?
Did you post the video of the last session? Because I couldn't see it.
Yeah.
Oh, right.
It's under evolution of physics.
Okay, I'll go and have a look. Thanks.
Yeah. All right. Well, if nobody has anything burning that has occurred to them.
I do. Hi, Eric. This is Martin.
Yeah.
I do have a question.
Okay.
In one of the readings, they're talking about thermic machines. I think it's Carnot. And at one point, it says something like, if you do not allow the and I might get this wrong because I'm a little bit confused about these concepts, but if you do not allow the excess heat or energy to escape a system, then the process cannot move forward. Does that mean that if you, for example, have a block, an engine block of a car, if you perfectly isolate the block in a way that it has a limit to the amount of energy it can radiate outside of the block, would that mean that eventually the engine would need to stop?
Well, I mean, empirically, it does happen rather rapidly. In other words, well, first of all, the generalization is, you've stated the generalization correctly.
Okay.
If you do not have removal of the heat, any engine will stop working. You have to have an energy flow for the engine to work.
Okay.
So in the case of an automobile, the actual cooling system is water circulating around the engine block into the radiator, and then a fan is blowing to cool that radiator. And so if that's interrupted, the engine will be destroyed fairly rapidly. As I know from personal experience, I was driving home at night from New York City on a highway. It was raining, and I struck an object that had fallen. It was a pretty small object, about this big, that had, I guess, fallen off a truck. It was a metal object. And I immediately pulled over and tried to survey the damage. Well, I removed the object, which had become stuck under my bumper. And I didn't see any visible damage. Now, I was worried because it struck in the area of the radiator. So as I was driving home, I was monitoring the heat gauge, because I felt that if the if there had been a leak in the radiator, then the heat in the engine would start to rise, and I'd pull over and get a tow from AAA. But the monitor remained perfectly steady. So I pulled off to the exit of my home, which was just a quarter of a mile from my home. Where I am now is just a quarter mile from the highway. And as I was pulling off the exit, the engine died. And so fortunately, I was able to walk home in a few minutes and call AAA. And they said that the engine was totaled because the object had struck both the radiator, putting a hole in it, and the monitor, disabling the monitor. So the monitor was no longer connected, and the indicator just was reading the same as what it had been when the accident occurred. So, yeah, since I was fond of the car, I got the engine replaced and bought another, newer used engine. But obviously what had happened was that as the heat builds up, the piston eventually starts to expand. And eventually this pistons just I won't say they melt themselves in place, but they essentially become eroded so that the engine seizes up. And once that happens, within seconds, the crankshaft bends. And once that happens, it's the engine is not repairable for less money than it costs to build another one.
And I do understand that, but hypothetically, were you able to build a thermic machine with materials that are way beyond that temperature, even if there were no physical damage, once there is no more flow of energy out, excess heat out of the system, the engine would stop anyways without destroying itself, because to do useful work, you need the flow of energy.
Right. You need energy ultimately to be flowing in a near equilibrium system where you can define temperature. It has to be flowing from a higher to a lower temperature. And that involves the idea of useful work. As we'll get into in a second, not all systems have defined temperatures, but you still have to be able to define energy flowing from higher energy density to lower energy density.
A gradient, you need a gradient.
Right.
Irrespective of your definition of temperature for the system.
That's right.
So, and the other thing, and I'll let you go, is that I need to declare that I have right now, I don't understand entropy fully in terms of thermal parameters. Rereading the material, I realized that my only understanding of entropy really is an information theory. Because my definition, from more information to less information, but that's the only really solid grasp of entropy I actually have, because when I read for the second time all the material, I caught a lot of nuances that I had overlooked in my first reading, and I realized I really do not understand some of the concepts, especially between the difference between useful energy and non-useful energy, and the internal energy of the system, which is not used to perform work. So I have a long way to go to really understand entropy properly.
Well, let's sort of get into that, because my first question, part of the readings deals with Boltzmann's effort to demonstrate, to derive the second law of thermodynamics from molecular dynamics, from molecular mechanics, based either on the readings or on your general knowledge. Well, let me take a step back. Any scientific calculation, any scientific theory inevitably involves a number of assumptions that are taken in order to characterize the equations that you use to derive your conclusions. So, what assumptions did Boltzmann make in this derivation? And if you want to elaborate, or we'll get into this as a second question, what limitations did that assumption make on the applicability of his derivation?
He assumed that the implications of Brownian movement and mechanics at the micro level would be translatable and imply a conclusion for the macro level.
Yeah, he did. He certainly did assume that. What else?
I don't remember. Anyone else?
Annette?
I'm trying to remember. It's been too long since I read it.
Oh, dear. Well, it's good that we're doing this review.
I think he was influenced by Darwin and the idea that I forget exactly. I mean, the main thing that I remember about Boltzmann is that he showed that it was statistically unlikely for things to become more organized, I guess.
Right.
And I remember it was sort of analogous to the approach Darwin had taken, but I'm forgetting exactly how that was.
All right. Well,
but he assumes a reversibility.
Irreversibility. Oh.
well,
No,
let me
never.
ask, let me give you a hint. What does he assume about the microscope? He is deriving the second law from studying the collisions of molecules with each other. Do you remember, does anybody remember the assumptions he makes about those collisions?
They're inelastic and mechanistic.
Excuse me, Martin?
They're inelastic, and he assumes a mechanistic approach.
Right. Yeah, he assumes inelastic. So inelastic means what?
That the collisions are perfect and there is no loss. No, sorry.
Right. So there's real molecules have internal energy, so that
conservation of energy, is that it?
what?
Conservation of energy?
Well, no, it's more strict than that. In other words, a real molecule is like two dumbbells on a spring. So in collisions, that internal energy can be excited. And so the energy into the collision, the kinetic energy into the collision can be more then the kinetic energy out of the collision,
Yeah,
because some of
yeah.
that energy becomes when the molecule is excited.
Yeah.
So for simplicity, he got rid of that. He assumed that these are little billiard balls that can't absorb energy internally.
So he assumed that the collisions were elastic,
Perfect. That's right.
perfectly elastic.
That's considered called perfectly elastic. All right. Well, maybe this is too technical a point, but it's a very important point. Unless anybody else want to say another assumption, because this was an explicit assumption. I think
Is
it
it
was one of the
is it
reasons.
something to do with the number of collisions?
No,
Oh.
no. I'll tell you.
Is this discrete, the discrete and continuous thing that he worked in discrete and continuous languages? So he assumed a discrete language for the micro world and a continuous language for the macro world.
Well, it was discrete in the sense there were discrete particles, but he assumed a continuous space. Well, look, I will give away the answer. The thing that was very important was that he assumed that the motion of the particles was uncorrelated. That is, that each individual molecule had a perfectly random, perfectly equal probability of being in a given direction relative to any other molecule.
Yeah.
So that's perfect uncorrelated motion. And in particular, he was assuming that the only interactions of the molecules were in the collisions. In other words, he was assuming no long range interaction.
Right.
So,
yeah.
given that assumption, based on our studies so far, what does that immediately what are some situations where those assumptions are simply not valid?
Well, if the particles in question have charge.
Right. In any plasma, there are long distance forces in which a particle, at one extreme, any particle in a plasma collection of charged particles contributes to both the electric and the magnetic field in the entire volume, theoretically in the entire universe. And that influence spreads throughout the volume at the speed of light. So that assumption right there is invalid for any plasma. But it's also invalid. Think of a very humble situation, a cup of coffee. If you take the cup of coffee and then, I don't have a spoon, you stir it. Well, during the period you're stirring it, you obviously see vortices form. Vortices, a vortex means that there is a high degree of correlation between the velocity vectors of molecules on average. Now, this might be at a small velocity relative to their thermal velocity, but it's quite significant. Now, of course, when you stop stirring, you'll find the vortices rapidly decay. And therefore you approach the situation where Boltzmann's assumption is again valid. But if you have a mechanical stir in there that is continuously stirring, which of course requires a continuous flow of energy to that mechanical stir, then you can have a long-term deviation from the assumption that there's no correlation.
Mm.
That's only true when there are no boundaries. Because if there are no boundaries, then the stirring never stops, does it?
No, that wouldn't be true. In other words, if you assume, without assuming no boundaries, if you assume the boundaries are very large compared with your stirring area, the vortex is still going to dissipate because of viscosity. And viscosity is basically a product of the random collisions of the liquid molecules with each other. So for any liquid with non-zero viscosity, and there are liquids that have zero viscosity, which is superfluids, but for a liquid with finite viscosity, then those vortices dissipate.
Yeah.
So those are, remember, we're talking about the middle of the 19th century.
Yeah.
So Boltzmann is operating in exactly the same period as Maxwell formulating the laws. So of course he was well aware of electromagnetism, but he chose, there was no such thing as plasma theory, and people hadn't really contemplated the existence for another generation of substances in which you had freely moving charges. But people had been studying for half a century moving charges in wires and their magnetic effect. And it was well known that these are long distance forces. But as was his right and duty as a scientist, any scientific formulation is going to abstract from certain processes, just like Galileo abstracted from friction in defining his initial laws of motion. But what's interesting is at the time when people were scratching their heads over this derivation, and they pretty much did scratch their heads pretty immediately, as far as I know, nobody said, oh, well, one thing that's limiting this is you're not considering electromagnetic forces, because people basically were overwhelmingly dealing with what we call neutral substances. That is where all the electrons are bound. So that's interesting because people very early on did say, well, how can you derive an irreversible process where time is obviously moving forward, the increase of entropy, the decrease in organization, from reversible collisions? Because people knew from mathematics dating back to Newton's day, that Newtonian collisions, the collisions of perfect particles, are based on reversible laws. So all those collisions, an individual collision, can follow the laws of physics if t is going forward or if t is going backward. It's the famous billiards. If you have just two billiard balls and you make a film of those two billiard balls colliding, you can't tell from the evidence of the film whether the direction of the film has been reversed. So that became an immediate paradox and people criticized him. As far as I know, people didn't say, well, you know, why did you leave out electromagnetic forces? So that's point one. The other thing is, and I don't think that this was in the reading, so I will introduce it, is that he assumed that any changes to this collection of colliding molecules was relatively slow compared with the process he describes as moving towards equilibrium. So what he demonstrated mathematically was that if you have this random collection and the initial conditions deviate from the Maxwell-Boltzmann distribution, and yes, Maxwell was working on the same problem at the same time, it will rapidly go back to the Maxwell distribution. And there's, you know, a time constant depending on how many particles you have and how fast they're moving, which defines how rapidly you have an exponential decay of the deviation from the equilibrium distribution. So an implicit assumption, right, as far as I know, he didn't make it explicitly, is that any changes of state to this collection, like heating it up or cooling it or mechanical motion, happened at a rate which was small compared to the time constant to decay towards equilibrium. Now, let me just, I don't want to confuse people. Does anyone not know what I mean by time constant? Okay.
Can you clarify that concept of time
A
constant?
time constant is just, if you have something that can be described by an exponential decay,
Oh,
then, you know, the time constant, if you think of the formula, e to the minus t over a, and a is your time constant. So time constant defines what's the time it takes to go 1 over e in a decay process.
okay, thanks.
So for example, now this is not a thermodynamic process, but radioactive decay, for example, the half-life is a time constant.
Okay.
It's mathematically slightly different than the time constant of, instead of the time to get 1 over E less radioactive substance, it's the time to get half the radioactive substance. But obviously, it's just a mathematical constant difference.
So each system has a particular time constant.
Right. So there's a decay towards this equilibrium.
Yeah.
Now, what he was implicitly closely aligned with his assumption of no coordinated motion was this assumption that any changes happen on time scales that are long compared with this time constant. And why are these correlated? Well, just think about it. Go back to my stirring. If you are stirring this on a time scale where the rate of energy that you're putting in to the stirring process is greater than the rate of energy that's pulled out by these random collisions, the viscous dissipation of the energy, then of course you're going to contradict his uncorrelated motion. If the time scale of your stirring is slow compared with the viscous dissipation time, which is the time, again, to get to equilibrium, then you're never going to form a vortex. So the kitchen analogy to this is look at the difference between stirring coffee and stirring honey. So if you stir a bowl of honey, you don't see a vortex being produced because the honey's viscosity is so high that the rate that energy is pulled out of your vortex is greater than what you're putting into it. While with water, coffee, tea,
So you need to stir at a higher radial velocity in honey.
That's right.
Vortex.
So, as I say, the implicit thing is that, and this is what really gets into the key limitation of the applicability of Boltzmann's derivation. If the time constant of energy flows through the system is smaller than the time constant of the return to equilibrium. So if the rate of energy flows is greater than the rate of energy dissipation, then you can have and maintain correlated systems of motion. And then the derivation simply doesn't work mathematically.
Yeah.
So given that, can people think of some examples of systems where the energy flow is large? I mentioned this distinction at the end of the last lecture class. What are some examples of systems where the energy flow is at a faster rate than the rate of return to equilibrium?
Sun to Earth.
Annette, what?
Sun to Earth. Like the Earth as a system and the energy from the sun in.
The sun to the Earth. Well, I'd have to think about it, probably. In other words, the yeah, that's probably a somewhat of a difference because we know that the Earth is at a very different temperature than it would be if it was a rock like the moon. It's much warmer, in fact.
An explosion, a chemical reaction that produces an explosion.
An explosive reaction, right? That obviously produces a situation that's very far from equilibrium.
Oh, okay.
Which, by the way, it's interesting. These, for the most part, if we look at 19th century technology, for the most part, we're describing systems that are undesirable from a technological standpoint. Remember, the chemical industry was developing rapidly in the second half of the 19th century. And the last thing the chemical industry wants is explosions, although it wasn't the last thing that they got. They got quite a few of them. So they wanted
So
About
there's a
nuclear
general.
decay?
what?
Nuclear decay? It adds energy as the
Well, now
nuclear-
that would depend on the rate of decay. In other words, if you have a long-term decaying process like uranium that has a half-life of billions of years, then it does reach equilibrium. In other words, there's an equilibrium level of uranium with its decay products. And it reaches an equilibrium of temperature with the surrounding rock. But obviously, if you had a very rapidly decaying
Isotope.
I mean, there are isotopes that decay in microscopic fractions a second, then you could get very easily a non-equilibrium situation. Two more examples.
It reminds me of the Bénard convection, where you heat a thin layer of water and the heat doesn't just
Right.
duct through it, but it begins to convect through these hexagonal cells that circulate up and down. So it's basically a structure emerges in the water. Or the
Right.
liquid.
And again, that's particularly if you have if you have a very large pot, you won't get those convection cells because the amount of heat, the flow of heat is small compared with the rate of evaporation. But in a normal pot, if you put it on, especially on the large burner or the large electric unit, then you do get convection cells, and you see it in the bubbling of not the bubbling, but the turbulence of the water.
Laminar flow going into turbulent flow.
Right. When you get beyond laminar into turbulent flow, you can get persistent structure, such as the vortices of a wing.
Yeah.
So two more obvious examples, and then we'll move on.
Excess neutrons in a nuclear reaction.
Well, again, it depends on the rate. If you're talking about a fission chain reaction, obviously you can get, again, an explosion, or you can get an equilibrium situation in a controlled fission reactor in which the generation of energy and heat are in equilibrium. Unfortunately, it's an unstable equilibrium, as we know. It has to be controlled by feedback mechanisms. Well,
Ocean currents.
Ocean currents, where again, you have the formation of long-lived structures.
How about like a storm system?
Right, same thing.
Runaway steam engine.
What about us, the participants in the discussion? Living things, right? Any form of life is a persistent structure that only maintains its existence by having energy flows that are sufficient to keep it away from equilibrium.
Yeah.
And I'll get into this later, but
Homeostasis.
one thing about Boltzmann's derivation is in a Maxwell-Boltzmann distribution where these assumptions are valid. In a closed system, energy flows continuously decay, ultimately, without limit, getting closer and closer to zero. But life, and I will get into in the 20th century the definitions of life, but life can actually be defined, and I think from a physics standpoint, it's a useful definition, as an organized system in which energy flows increase with time without limit.
Well, that's kind of what I meant when I said the sun. I was thinking of the sun as the source of energy that.
Right, but if we look at the sun, well, that gets it. The sun is an example of my second example, which we should have, because we've talked a bit about it. It's plasma. Obviously, in a plasma, you have long-range correlations based on the long-range electromagnetic forces. And in most real plasmas in the universe, the empirical rate of energy flow is very great compared with the dissipation forces, which in most plasmas in the universe are very small because of the extremely low density of the plasmas. The sun is a plasma, it's actually a high density plasma. And what we see in plasmas, such as the plasma in our Focus Fusion 2B device, is that plasma processes can lead spontaneously to a very great increase in energy flows. But unlike in light, the increase is not without limit. So in the plasma focus process, as an example, you have a process lasting over microseconds in which energy spontaneously through the pinch process is increased until you have the extreme high energy density of the plasmoid. The plasmoid emits beams and generates fusion energy, but the process is self-limiting. In general, the process only lasts at maximum a few thousand times what you call the energy crossing time, the amount of time it takes energy to get from one side of the process to the other. But with life, we have evidence from the one place we know life exists, Earth, that this process of increasing energy flows can continue indefinitely for billions of years in what you could call contiguous parts of space. That is contiguous in the sense that every living cell is derived from a continuous transformation of previously existing cells. So plasma and living organisms are two big exceptions where the assumptions clearly don't apply. In the case of plasmas, it's because of the long range forces which can cause long range ordering, vortexes, filaments, plasmoids. In the case of living beings, it's because the structure of the cells itself orders down to a molecular level the motion of the molecules. Like, for example, in the earliest cells, which are still with us as a form of bacteria, this is something I learned only in the last decade. The energy source of the cell is located on the cell membrane. So the cell, by its structure, forces protons from the water molecules to cross the membrane in one direction, and electrons at a different point of the cycle, electrons to move in a separate way, so that the charge on the tiny charge on the bacteria is maintained, and they actually maintain an electric gradient that drives the chemical reactions within the cell.
Wow.
So this is something where a non-equilibrium, a coordinated non-Maxwellian motion of individual molecules is maintained by the structure of the cell. And the structure of the cell, in turn, is maintained by the energy released by this coordinated process. So these exemptions from the assumptions are some of the reasons that resolve, in part, the apparent paradox of Maxwell saying all closed systems should run down, which was fine technologically, that was clear, but it became paradoxical when it was applied to the universe. That got the heat death of the universe, and yet this was in the context where everybody was paying attention to the Darwinian story of evolution, which obviously was the exact opposite, the development of more and more complex
I have a question about
structures.
the life as a biomass is not a closed system, isn't it?
No, but the question is, how does this whole process get started? Now, fast forward to the late 20th century, and people will say, well, you know, all bets are off at the Big Bang. You have the Big Bang being creating the universe in a low entropy state. But this is long before this. We're talking about the 1860s. And the 1860s, there was no scientific conception of a finite age of the universe. And I want to step back just before going on and into this paradox as they saw, into the cultural context. I mean, Darwin's work very rapidly became central to the intellectual life of the world in the mid to late 19th century. First of all, because it became a big point of conflict with organized religion. Initially, organized religion in the mainly Christian countries completely rejected Darwinism because of the origin of not the origin of the species, but the later book, the Descent of Man. So the idea that people were descended from other animals and not from Adam and Eve was considered blasphemous. So back then, you immediately had this big cultural conflict between organized religion and the scientific community almost as a whole. At the same time, you had people from many different standpoints looking at Darwin's work to fit into their own political conceptions. So, for example, Marx and Engels took most of Darwin's work as a generalization of their theory of social evolution. Biological evolution the same way. Now, they explicitly rejected Darwin's limited resource survival of the fittest explanation of the mechanism of evolution. So they said, well, he got that clearly from Malthus. But many other thinkers at the opposite end of the political spectrum glommed onto that, and out of that was the development of, does anyone want to say? Name two political conceptions that came out of Darwin.
Hegelian dialectics.
What?
Hegelian dialectics.
No, Hegel is long before Darwin.
Oh, before, yeah, sorry.
No.
I have time dyslexia.
Social
Eugenics.
What?
Social Darwinism.
Social Darwinism, obviously. So the idea that economics is a competition for limited resources, and those who come out on top, in other words, the rich, deserve it. And anything that stands in the way of competition, except things that help the rich, is good. It would be bad. And one other ideology, which unfortunately is still with us,
Eugenics.
Eugenics, right?
scientific racism. Eugenics is a part of that. We have in Germany the top popularizer of Darwin in Germany, Ernst Haeckel, is also a leading theorizer of a really vicious form of scientific racism, in which he claimed that the races originated separately, which Darwin did not. Darwin said that humanity is all has common descent, even though he said that it's now distinguished into races that can be ranked hierarchically. But Haeckel said these are separate species. And in the case of Africans, I think even a separate genus, not human beings at all. And this very rapidly was adopted to modernize the ancient anti-Semitic prejudices of the day. And during the decades following, pretty substantial amount of time, 40, 50 years, the development of scientific racism and the merger of what you would call state anti-Semitism from the Russian Empire, such as the forging of the Protocols of Zion. This merged into basically the ideology that Hitler popularized as Nazism. So this question of evolution during these last third of the 19th century and into the early 20th century really became dominant. And it's an unfortunate point. Maybe people can contradict me, But in my readings, by the end of the 19th century, almost all prominent intellectuals endorsed in some way racist theory when they were at all commenting on human differences, with the exception of people, scholars of African descent and socialists and communists, and anarchists like the IWW. So only people, by the early 20th century, only people who identified racism as a pro-capitalist ideology that needed to be fought, and the African Americans who were at the receiving end of most vicious of this, these were the only public intellectuals that were actually condemning racism as a complete, in a complete way. The situation, as far as my research goes, didn't really start to change until the 1930s and the rise of the rise of mass radical movements in response to the Depression, and the rise of opposition to the Nazis and the beginning of the discrediting of their racial theories, which really didn't thoroughly happen until after the defeat in the Second World War. So that's some of the background to the question of putting together Darwinism. But the paradox that was seen, including by Boltzmann, is if you have a universe that has existed, presumably indefinitely, it should have in that time had plenty of time to decay to perfect equilibrium. And yet that's not what was observed. Obviously, people saw that we have in the universe flows of energy that are very large. And although they weren't, again, as far as I know, using this direct comparison of the flow of energy versus the rate of equilibrium, they were showing that this was a source to drive thermodynamic processes. But again, it seemed totally paradoxical, because when thermodynamics was applied, for example, to the sun, Eddington used simple calculations to show that the sun would have a very short lifetime in geological time, a few million years, if the source of energy was any source then known to human beings, like if it was made of solid coal, hydrogen reacting with oxygen. None of these would give the time scale that geologists were simultaneously finding of hundreds of millions of years. So by the late 19th century, geologists had already shown by rates of sedimentation, before there was any knowledge of radioactivity, that the Earth must be hundreds of millions of years old. But Eddington was showing on the basis of thermodynamics that the sun was millions, could not have survived for more than a few million years. So that's where the paradox was coming. Where did these sources of energy come from? Okay, so any questions and comments on this?
Yeah, I do have. So discarding the Big Bang, we're sort of looking for some kind of prime mover that can reverse entropy in certain parts of the universe and for certain time.
Well, but that's the point, isn't? In other words, the analysis, the mathematical analysis that Boltzmann was basing does not apply to the universe that we actually observe.
Yeah.
Because, first of all, the universe is blessed with not just one, but two long-range forces.
Mhm.
As far as we know, both electromagnetic forces and the force of gravitation do not, to our present knowledge, have limits in range.
Mm.
Now, the series I've been working on, but I haven't gotten time to finish, which is the companion piece to this one, which I just reversed the order of the words, the physics of evolution, describes what we know of the evolution of the universe, not assuming an origin in time. And even in the first episode, which is on our YouTube, I described that if you have a gravitating plasma, the natural evolution of that plasma is through the pinch effect to form organized currents. This is over vast periods of time, that currents that can start out randomly, since currents moving in the same direction attract, and currents moving in the opposite directions repel. A plasma naturally tends to form plasma filaments. And under the influence of gravity, these plasma filaments, which are concentrations of matter, break up into more concentrated disks. The disks, in the interaction of the gravitational forces with the magnetic forces, form smaller networks of filaments, and the process actually descends to the point where you have very big energy flows, very dense and very complex structures, and the process, that process terminates in the production of stars, where the production of energy increases further, because for the first time in stars you have the production of fusion energy. So in a general sense, you can see the production of structure and the increase of energy flows, not without limit. These are all self-limited processes. But the increase of energy flows, a transition away from equilibrium in processes that can be followed just with known laws of electromagnetism, plasma physics, and gravitation. And by the way, when I refer to the fact that people didn't point to electromagnetic forces as a limitation, you have to realize at this point, nobody had, remember, we're in a period before the discovery of the electron. So it isn't even known that electricity has particles associated with it that can move independently. It was known that, you could have electric currents, but at that time, it wasn't clear whether this was particles moving and a fluid moving or what, even, after the development of Maxwell's theory, because Maxwell's theory, you could understand Maxwell's theory without hypothesizing charged particles. Now, people were approaching that because they knew from the evidence of chemistry, there was accumulating evidence of the existence of atoms. So and they knew that atoms through chemical reactions could exchange charges. So this knowledge was accumulating, but it wasn't until the end of the century when people started to experiment with flow discharges, which I mentioned in one of the earlier sessions, that led to Thomson's discovery of the electron. But with our knowledge just of the existence of electrons and protons in a hydrogen plasma and the electromagnetic laws and Newtonian gravitation, then you can get this evolution from a more uniform, less structured universe to a much an elaborately structured universe that looks pretty much like what we see today.
So is that then the answer to the question that was in the Kelvin reading, where he's wondering about where the energy that's powering the sun is? Is it because it's the natural termination point of like this big current, like space current of energy flowing? And it
No,
just-
I mean, was it Kelvin that did am I misstating?
it was
Was it Kelvin who did the calculation on the sun?
Sir William Thomson.
Yeah, I'm sorry, then my mistake. It's Kelvin. But it is related because Eddington popularized the idea of the heat death of the universe. No, I mean, we know today, obviously they couldn't possibly know in the 60s and 70s of the 19th century, the source of energy of the sun, which is self-limited, but over billions of years of time, is fusion reactions within the sun that convert hydrogen into helium. The energy flows were necessary to concentrate the matter that gave rise to the sun and all the other stars. And in particular, one of the things that my mentor Alfvén described in starting to outline this process, it was only electric currents concentrated into these vortex filaments that allowed the efficient transfer of angular momentum from the contracting stars to the surrounding plasma. So that was one of the paradoxes of star formation way into the 20th century. And in fact, beyond the point where Alfvén solved this, because many people ignored Alfvén's work in the late 20th century, but people could easily calculate that if you take a light year, essentially, of matter in the galaxy, you've got about, if you've got a cubic light year of matter in the galaxy, you've got about the mass that would create a star the size of the sun. Well, the galaxy, we all know, observations show, is rotating very slowly. One rotation is about 200 million years. And the galaxy has only rotated, a few dozen times in its lifetime. But you can take the angular momentum of this cubic light year of matter, which is rotating with at least as fast as the galaxy. It may have its own rotation. So angular momentum, remember, is the product of mass, velocity, and radius. So these radii are very, very great. A light year is 10 trillion kilometers. People can correct my number of zeros. If you compare that to the angular momentum of the sun, or even the maximum angular momentum the sun could have without tearing itself apart, without exceeding its escape velocity, it's millions of times bigger. So the question is, since angular momentum is conserved in an isolated system, how is that angular momentum conveyed from the contracting system? And the paradox was it couldn't be by viscous forces. It couldn't be by like what happens in my stirring example, because the viscosity of plasma in space is insignificant because there's so little of it. The density of plasma is approximately 1/10 of an atom per a cubic centimeter. So viscosity doesn't work. And this became a big paradox until Alfvén started saying, well, the rotation, there are magnetic fields in space, wherever we look, the rotation of a body, a conductor, in a magnetic field produces a current. This was the Faraday disk generator, discovered obviously by Faraday.
And that transfers the angular.
So that current, Alfvén and Feldheimer showed that current inevitably produces filaments. So these filaments become like swinging baseball bats, and they are very efficient at conveying energy, angular momentum, from the center of a disk to the outskirts, so that more as the volume contracted, more and more of the angular momentum was moved to the outer layers. Those eventually escaped because they had so much velocity, they escaped the gravitational field, rejoined the interstellar medium. And that continued down to the point at which a very dense solar disk was formed. And at that point, and again, this is stuff that was worked out in mathematical detail by Alfvén and his collaborators, some of these filaments started to condense into the nuclei of the major planets, like Saturn and Jupiter. And within the solar system, we see that the vast majority of the angular momentum in the solar system is not possessed by the sun, which has almost all the mass in the solar system, but is possessed by the major planets. Most of it is Jupiter's angular momentum around the sun. So all of these processes are based on not being in accord with the assumptions. And again, these were assumptions that Boltzmann made to simplify the calculations, and because he felt they were justified in the phenomena he was studying, such as heat engines, chemical reactions. But in the universe where we have charges that are free to move, and thus creating magnetic fields that have long distance correlations, and we have the long distance correlations created by gravity, then if the assumptions are not true, the derivation is not true. You have no tendency to destroy order and to decrease energy flows. What you do have empirically in non-living matter is that this increase in energy flows is limited on its own time scale. So these are very long time scales, but clearly the time scale of the formation of the largest structures of the universe, which are things like the recently discovered Big Ring, discovered by Alexia Lopez earlier in this year.
Mm.
These are trillions of years. So they're very long time scales, even compared with the lifetime of a star like the sun. But they're not infinite. These processes have essentially beginnings, middles, and endings. And that's true for stars as well. Any individual star has a natural lifetime, which is, in the star's term, only a few thousand times the energy crossing times. In other words, if the sun suddenly stopped producing energy, it would take a few million years to cool down, as Lord Kelvin calculated. So its actual lifetime, which is about 10 billion years, is only several thousand times its natural equilibrium rate or time scale.
Mm.
For reasons that
I'm confused.
are not entirely worked out, you see this throughout plasma phenomena. The transient phenomena last at most a few thousand equilibrium timescales. But as we'll get into in future, even that consistency is broken when you get into living phenomena, where we know empirically that biosystems can survive for many trillions of time their equilibrium time. I mean, you can imagine how short a time it takes for a dead bacterium to reach equilibrium. I suspect it's of the order of milliseconds. But we know that bacterium's descendants have increased energy flows on the Earth many, many fold over billions of years. So again, if the assumptions are incorrect, then there's no contradiction, but the conclusions are also incorrect.
Mm.
So any further?
Eric, yes. Eric, I was going to ask whether Einstein created a sort of most general case in E equals mc squared that essentially matter and energy are interchangeable indefinitely.
Well,
and that's the ultimate refutation of Boltzmann.
It's not indefinite because, as I say, any process, any non-living process, the energy flows have a characteristic time in which they increase and then they do decay. So, for example, a star which is converting a significant fraction of its matter into energy, approximately 1/10 of its matter becomes converted into energy when all of its hydrogen is burned into helium. Nonetheless, that has a finite endpoint. In other words, a star like our sun, I'm not talking about our sun in which we're projecting it into the future. I'll get in a moment the problem with doing that. But if we take a star like our sun that has existed in the past, that has already had its lifetime, as its hydrogen core becomes completely converted into helium, a helium core then is heated to higher temperatures, and a new reaction takes place that converts the helium into carbon. And this burning continues until the end point is
Iron.
Iron.
the end point is iron, but that's only reached, right. The end point is iron, and immediately when the end point is reached, the inner core of the star, which of course has to be in equilibrium with the enormous weight of the star on top of it, no longer can support that weight, which is being supported by radiation pressure from these fusion reactions. And you get a core collapse supernova.
Yeah.
Now, in the case of a star the mass of our sun, the end isn't that spectacular because of its smaller mass. It actually just blows off in a process lasting millions of years, its outer layers. And we observe these phenomena as planetary nebula.
Brown dwarfs.
And then eventually it collapses into either a neutron, either a white dwarf or a neutron star.
Oh.
But a larger star, more than 15 times the mass of the sun, that produces these supernova explosions. So as I say, when we're dealing with non-living phenomena, all of these phenomena, while they have significantly long periods, thousands of times their natural equilibrium period, where they move away from equilibrium, they don't move away from equilibrium indefinitely. What's interesting, and I get into this in the video series, is if you look at the universe as a whole, these self-limiting series, self-limiting phenomena form a series, and the series itself involves accelerating energy flows. So the process that forms these large-scale structures is much slower than the similar process that forms the clusters, what will eventually be clusters of galaxies, and a still faster process forms the galaxies. Still faster process forms stars within the galaxies. So there's this continuous acceleration. And of course, we are part of that acceleration because we've now moved from biological evolution to an additional stage of evolution, human social evolution, of a time scale of decades or centuries, which is what makes it really ridiculous when people talk about, the Earth will burn up to a cinder in 5 billion years, which doesn't take into account that, you're discounting the dominant process in terms of the solar system's evolution, which is human social evolution. Human social evolution is increasing energy flows on Earth at a rate that is many orders of magnitude faster than the rate of evolution of the sun. And people pointed out, there was a Sky and Telescope article that I liked that made fun of this, that said that if a future civilization, 10,000 years in the future, which is longer than civilization has existed by a factor of 2, started to get worried about this distant problem of the sun heating up in billions of years, simply by diverting the orbit of an asteroid to move in front of the Earth once every 10,000 years, you could engineer the Earth to move away from the sun in such a way that its climate would be fine-tuned to the billion year evolution of the sun. The key point I'm making is that processes are defined necessarily by the fastest energy flows, or the fastest rate of change of energy flows. So if you're studying a solar system in the distant past, the time scale that is useful to study might be the evolution of the star. If you're studying a galaxy, it might be the much longer time scale of the evolution of the galaxy. But if you're studying this solar system and you ignore the phenomena of life and human civilization, then you get ridiculous answers because you're ignoring the dominant process in terms of the rate of evolution. So let me just say, because we're reaching the end of the time, that we are going to revisit these subject of non-equilibrium thermodynamics in the chronologically appropriate point, which is the second half of the 20th century, when Ilya Prigogine and collaborators started to realize the shape of the answer to the paradoxes that had been raised almost a century before in thermodynamics. Interestingly, these solutions, even though Prigogine, like Alfvén, won the Nobel Prize, these solutions are not universally accepted in the field. But as I say, we'll get into that in a chronologically future study group. Right now, we're going to say goodbye to the 19th century, which in physics terms we define as ending in 1895, because all of the big discoveries of X-rays, the electron, plasmas, start in 1895. So we sort of have the long 20th century. And I think we're going to start by getting into the developments that lead towards quantum mechanics. We have to study separately several contemporaneous revolutions because, of course, as people know, quantum mechanics, special relativity, general relativity, plasma physics are all developed during this revolutionary period that extends essentially from 1895 through the early 1930s. So we're going to get into that revolutionary period next time. Okay, thanks all.
Thank you, Eric.
Thanks,
Bye,
Eric.
thank you.
Everyone.